Welcome to Institute of Quality and Reliability. Hi, this is Hemant.
In this video, we will discuss homogeneous Poisson process or HPP and non-homogeneous Poisson process or NHPP. First, we will discuss the homogeneous Poisson process. When parts are repaired or replaced in a repairable system, it is considered that the system is as good as new. Such a process is called renewal process. When hazard rate lambda is constant, mean or expected number of failures during time t will be lambda t. This is called homogeneous Poisson process, HPP. But we must understand that lambda t is the expected number of failures. Actual number of failures in HPP will vary randomly and will tend to follow Poisson distribution. Therefore, probability of k failures during time interval t can be estimated using Poisson distribution as follows. Probability of k failures equals e to the power minus lambda t raised to the power k divided by factorial k, where k is the actual number of parts failing during time interval t and lambda being the constant failure rate. Viewers can watch our video on Poisson distribution for better learning experience. Link is provided in the description. HPP is widely used for repairable equipment and systems throughout the industry. The homogeneous Poisson process HPP model applies to the flat portion of the bathtub curve. Many systems or complex tools or equipment spend most of their lifetimes operating in the long, flat, constant repair rate portion of the bathtub curve. The HPP is a popular model for system reliability evaluation and system test planning. The HPP is also used in modeling many other processes. Many of the mill standards also used the homogeneous Poisson process as the basis. Let us now see a simple example of homogeneous Poisson process HPP. A battery of 10 machines have mean time between failures of 500 hours. What is the probability of 4 failures in 1000 hour operation in one single machine? MTBF is equal to 500 and therefore failure rate lambda is equal to 1 upon 500, that is equal to 0.002. Therefore expected number of failures during the interval of 1000 hours is equal to 0.002 into 1000, that equals 2. But we want to find probability of 4 failures. In one machine, probability of 4 failures will equal e to the power minus lambda t raised to k upon factorial k, where k is equal to 4. We substitute lambda t equal to 2 and k is equal to 4 and get the answer as 0.09022. And this is the probability that we will have exactly 4 failures during an interval of 1000 hours of operation of one particular machine. Now let us see non-homogeneous Poisson process or NHPP. When failure rate varies with time, rate at which failures or events occur will also vary. Such a process is called non-homogeneous Poisson process or NHPP. In repairable systems, time to first failure may be modeled with exponential or Weibull distribution. However, the times to subsequent failures do not usually follow a single distribution. Times to subsequent distributions are called inter-arrival times. In reliability, NHPP is used to model systems when failure rate varies with time and does not remain constant. This is commonly observed during design and development of systems when the reliability improves from start of project to the end of project as design improvements are made whenever failures are observed and corrective action is taken. To model NHPP, failure cumulative intensity function M of t is defined as M of t equals integral of 0 to t M of t dt, where small m of t is instantaneous intensity function and m of t will be derivative of the cumulative intensity function, that is d capital M of t by dt, where capital M of t is expected number of failures till time t. In non-homogeneous Poisson process or NHPP, two models are commonly used to characterize failure intensity function. The first one is power law model, according to which the capital M of t, the cumulative intensity function, equals a into t raised to b. If we take logarithms, ln of m of t will be equal to ln of a plus b ln t. Based on this, the instantaneous intensity function will be given by derivative of the cumulative intensity function, and that will be equal to a into b into t raised to b minus 1. The second model used is exponential model, according to which m of t equal to a into e raised to bt. Or if we take logarithms, ln of m of t will be equal to ln of a plus bt. If we take derivative to find out the instantaneous intensity function, it will be equal to ab e raised to bt. In the above models, a and b are constants that are estimated numerically or graphically from data. In power law model, where b is less than 1, system is improving over time. That is, failure rate is reducing over time. When b is greater than 1, system is deteriorating over time. NHPP is used in reliability growth models including Diwan and Crow-AMSA models. We will see these models in our subsequent videos. In repairable systems, the time to first failure may be modeled with exponential or Weibull distribution. However, the times to subsequent failures do not usually follow a single distribution. Times to subsequent failures are called inter-arrival times. You can see figure below to understand this concept of inter-arrival time. In an NHPP process, the expected number of failures between time t1 and t2 will be given by the difference between the cumulative intensity functions at these times, which can be written as capital M at t2 minus capital M at t1. For relatively small time intervals, failure rate may be assumed to be constant, and probability of k failures in time interval t2 minus t1 can be estimated using Poisson distribution, and that will be given by the following formula. Note that the mean of this distribution is m of t2 minus m of t1, and a number of failures for which we are determining the probability is k. Let us see an application example of non-homogeneous Poisson process. A repairable system has cumulative failure intensity function capital M of t equal to 0.007 t raised to 1.3. This is a power law function. Question 1. What is the instantaneous failure intensity function M of t? Second, what is the expected number of failures during time interval 50 to 100 hours? And question number 3. What is the probability of no failures during the interval 50 to 100 hours? Capital M of t is equal to 0.007 t raised to 1.3. If we differentiate this, we get the instantaneous failure intensity function small m of t, and we get 0.007 into 1.3 into t raised to 1.3 minus 1, which works out to be 0.0091 t raised to 0.3. The expected number of failures between 50 to 100 hours will be given by the difference between the function capital M of t for 100 and 50. So we calculate the function at the two time values, that is t1 and t2, to get expected number of failures during the interval as 1.65. Now to answer the third question, we need to use this expected number of failures for finding out probability of zero failures. So probability of zero failures in time interval 50 to 100 can be estimated using Poisson distribution, and that can be equal to probability of zero failures is equal to e to the power minus 1.65, 1.65 raised to 0 upon factorial 0, which equals e to the power minus 1.65, as factorial 0 is equal to 1 and 1.65 raised to the power 0 is also 1. We can calculate this as 0.191. Note, probability of zero failures in an interval can be considered as reliability of the system during that interval. Let us do a quick recap. The homogeneous Poisson process, or HPP, is applicable when failure intensity is constant. The HPP model applies to the flat portion of the bathtub curve. Many systems or complex tools or equipment spend most of their lifetimes operating in the long, flat, constant repair rate portion of the bathtub curve. The non-homogeneous Poisson process, or NHPP, is a useful model when failure intensity varies with time. This is typically the situation during design and development when design improvements are made during testing. We have also discussed application examples of HPP as well as NHPP process.
Thanks for watching this video. Hope you found it worth watching. Please subscribe to Institute of Quality and Reliability channel if you want to watch more videos on reliability engineering, Six Sigma, and statistical quality control. Thank you.